Welcome back everyone. Today we are going to discuss about the concept of solid angle. I'm going to cover all the applications of electrostatics and optics. So first off, what is a solid angle? So a normal angle was just a two-dimensional angle. So if we take some kind of object like this, the angle between those two objects was some angle theta. But three-dimensional angle was the solid angle was the angle which was three-dimensional. Two-dimensional mean if we take these two objects, then the angle between them becomes theta. But three-dimensional angle, solid angle was the entire angle. I think you got the intuition, right? So the normal angle have units as radians. But solid angle have the units steradians. So if we take, let's suppose, a cone, then the solid angle enclosed by the cone can be the area of the circle which was in this direction divided by the distance from which we were measuring the solid angle square. So let's suppose this is R1 and this is R2, and then this would be A2. So then solid angle equals to A1 square by A1 by R1 square equals to A2 by R2 square. This is solid angle. So now we are going to discuss about the relation between a cone, half angle of a cone and solid angle at its vertex. Okay, now we are going to discuss relation in half angle of cone and solid angle at vertex. Before that, I want to conclude that if there was a surface like this and if there was an area like this which was not normal to the surface, then we need to resolve this into a component which is normal to this. So in this case here, solid angle equals dA. We are taking a small area here, so that's why it is dA. So here solid angle will become dA cos theta by whatever distance this is at, R square. So now relation in half angle of cone and solid angle at vertex. We are finding the relation between half angle of cone and solid angle of that cone. So let us assume a cone. So let us think there was a cone like this. And this is theta and this is theta. So to solve this, we are assuming a sphere. We are assuming this cone was enclosed in a sphere. So for which this is going to be the center point. So we are assuming a sphere of radius r. The sphere ain't perfect. So we are assuming this is the center point, which doesn't look like the center point. And we know that the solid angle this makes is exactly the same as this cone makes, right? So we want to find the solid angle by this surface. So we are gonna divide this into infinite small rings and integrate it. So let us suppose this is a sphere. And this is our cone. Let us think this is the center. So this is theta. Let's assume from here at an angle phi there was an elemental ring. So by trigonometry we can say the radius of the elemental ring is r sine phi, right? So our goal is to find the area of this surface by which we can find the solid angle. So it is going to have a small thickness of angle d phi, right? So the length of that width is going to be r d phi. So the area of that elemental ring is going to be ds equals to, ds in the sense this is surface area, 2 pi r sine phi. Don't confuse this with the electric flux. And multiply this with r phi, r d phi. So we need to integrate this in order to get the area of this whole thing. 2 pi r sine phi is basically the circumference of this elemental ring times the width, which gives us the area of the elemental ring. So On integration, we should take the limits from 0 to theta. Let's suppose this is just 0 here. So we can separate the constants from the integration part. So which was just 2 pi r square, and integrate the sine phi with respect to phi from 0 to theta. So integral of sine phi was negative cos phi. So 2 pi r square of minus cos phi from limits 0 to theta. Right? So here, after substitution, this will become 1 minus cos theta of 2 pi r square. Or vice versa, 2 pi r square of 1 minus cos theta. So finally we can substitute in this. So solid angle equals s by r square, which is 2 pi r square of 1 minus cos theta divided by r square. We can cancel out the r square terms, and solid angle will be 2 pi of 1 minus cos theta. So we established a relation between half angle cone, which was theta, and solid angle of the cone. So with this we can also calculate the electric flux of the electric flux passing through a cone if an object was placed somewhere here. Let's assume there was a circle. And at some point here, at some distance a, there was a point charge plus q. So we need to find the electric flux through this. So this was basically a cone, right? I mean, the electric flux would be same if it was a cone or circle. So the electric field lines will be in all directions. So if we compute with this equation, through a spherical surface, the solid angle will be 4 pi. So flux per solid angle will be, flux per solid angle will be q by epsilon naught into 1 by 4 pi, because if we assume a sphere here, the electric flux through this will be q by epsilon naught. So for unit solid angle, this will be q by epsilon naught into 1 by 4 pi. So for this surface, it would be q by epsilon naught, 4 pi epsilon naught times the solid angle of this, 2 pi of 1 minus cos theta. So this would result in this solid angle, flux through the cone or the circle will be q by 2 epsilon naught of 1 minus cos theta, where cos theta equals to, here this is theta, so a by root over a square plus r square. So we figured out the flux through the cone, which was a lot simpler using solid angle than the manual approach. So now we are gonna solve a question. So the question was, the point source of light is at a depth h from the surface of water body. If power of the point source is 100 watts, find light power which reduces out from the top surface. So here we are basically not assuming the power loss due to refraction. So it's a good idea for you to solve it by pausing it before I explain the solution. So this was a slab made out of some material which have a refractive index of 5 by 3, and here it was vacuum. So this was the point source of light. So the light is going to refract, making some angle in both directions until it reaches the angle with normal equals to c, the critical angle. Then it just grazes over the surface, and if the angle was above c, it will just total internal reflect. So c is just sine inverse of 1 by mu. So here the value of mu was 3 by 5 by 3, so the value of c was sine inverse of 3 by 5. So c equals 37 degrees. So this was basically a cone, right? So if this was c, then this would also be c. So we can use the result we previously got. Solid angle equals 2 pi of 1 minus cos theta. So if 100 watts was, in all directions, we found the solid angle for a closed surface was 4 pi, right? We can use that. So flux, sorry, no, not flux, the power cone equals 100 divided by 4 pi times 2 pi of 1 minus cos 37 degrees was 4 by 5. And this was 1 by 5. 1 by 5 times 1 by 2 is 1 by 10. So this would become 100 divided by 10 watts. So power through this cone surface was 10 watts. So let's get to our next question. So if there was a cylinder like this, and at the midpoint there was a charge of plus q charge placed in the cylinder, and this length was rho 3r and this length was rho 3r, and the radius of the cross-sectional area was r. So we need to find the flux through curved surface. So we can find the flux through this circular surface easily. So first we need to find the angle theta. So this was root 3r and this was r. So by this we can say that I cut the video for some reason, so let's continue. So here we can say that sine theta equals to this was the hypotenuse, so 3r square plus r square equals to 4r square, and square root of that was 2r. So sine theta was r divided by 2r is equals to 1 by 2. So theta was pi by 6. So by this we can substitute this in the solid angle formula, as we know the relation between this and solid angle. So flux through one circular surface was one by 4 pi, because through a whole surface it was cube epsilon, through whole surface the solid angle was 4 pi, and we need to multiply that with the solid angle of the circle. So that is 2 pi of 1 minus cos theta, which is root 3 by 2. And the flux through curved surface will be flux through the whole surface, which is q by epsilon naught minus 2 times this, because there were 2 circles. So this will be q by epsilon naught of 1 minus root 3 by 2. So finally the flux through curved surface will be root 3 by 2 q by epsilon naught. So let's approach the last question of this video. So if there were 2 charges, plus q1 and minus q2, and if a line of force was emerged at an angle alpha at q1, at what angle will it terminate at q2? So there will be many field lines produced by this charge, and not all of them will reach q2, right? Only some of them will reach q2. I mean negative q2 in the sense. So how many field lines that's gonna go from here to here will be the same. I mean, if we assume an angle alpha here, at an angle alpha, the number of field lines that were going from here to here will be same as the number of field lines it was receiving, right? So we are going to equate flux here and here. So we should not take the whole flux. We should only consider it for the angle alpha. So q1 by epsilon naught into 1 by 4 pi into 2 pi of 1 minus cos alpha equals to q2 by epsilon naught of 1 minus cos beta into 1 by 4 pi. Let's suppose this is some angle beta. So we can cancel out these terms which were in common. Now we can apply the trigonometric identity, which was 1 minus cos theta equals to 2 sin square theta by 2. So q1, 2q1 sin square alpha by 2 equals to 2q2 sin square beta by 2. We can cancel out the 2 here, and from this we can say that sin square beta by 2 equates to, or let's just do the square root. So sin beta by 2 equates to square root of q1 by q2 times sin alpha by 2. So we can just apply the sine inverse of this, and it will make the value of beta as 2 times the sine inverse of square root of q1 by q2 times sine alpha by 2. I hope this video was clear, and that's it for this video.